Hello everyone, we're going to look at properties of salts and the pH of the solutions that they make. You may not realize that when you put salt into an aqueous solution, it can impact the pH of that solution. So we're going to take a look at that. We're going to look at the properties of salts that make it unique and how to determine these pHs. And one of the properties of salts is, first of all, what is a salt, right? A salt is going to be anything that has a metal attached to a nonmetal or a metal attached to a polyatomic. So visually you can recognize a salt. So salts are ionic, which means that when they go into an aqueous solution, these salts are going to separate into ions, 100% into it. We are looking at soluble salts, and later on we'll look at insoluble salts that actually need a K value. So these are all soluble salts, which as soon as I put them in, all right, so let's say I have something like this, it's going to 100% be as ions, so I won't have anything left as the molecule of salt. They form strong electrolytes because they make ions, and really where they came from was from an acid-base reaction. So here's a typical acid-base reaction. Here's your base, here's your acid, and it always makes something called salt and water. So I'm going to write water as HOH. This is a double replacement reaction, which means that those cations switch places. So the Na is going to come over here, and then the H is going to come over there. And you can see how that H grouped together with the OH from the base to make water, if I write it like that. So acid and a base always make salt plus water. So in this salt, look at where these ions came from. The metal part of the salt, because that's part of a salt, right? Metal and a nonmetal. The metal part came from the base, and the anion part came from the acid. So kind of think about that. The metal part comes from the base. The anion of the salt comes from the anion part of the acid. Okay? So let's look at salt hydrolysis. Describes a reaction of an anion or cation of the salt reacting with water, and from that they can affect the pH. So the first thing we need to do is classify what type of salt we have so we can look at how their cation or anion of the salt can impact the pHs. So we have these four categories of salts, and what we're saying is these are the parents of the salt. So salts are metals and a nonmetal, but where did they come from? Did they come from a strong acid and a strong base? Did they come from a weak acid but a strong base? So in this one, this is a strong base and a strong acid. This salt then is an SASB or SBSA, means the same thing. That's the type of salt that this is. It's a strong acid, strong base salt because its parents were both a strong acid and a strong base. All right, in order to do this, you have to know those lists of the strong acids and the list of the strong bases. Let's take an example of how a SASB salt can impact the pH. I honestly don't have any of these memorized. I just kind of work out the hydrolysis reactions and it tells me what type of pH it's going to be. So there's concepts here to determine those pHs, and this is a concept. The strong acid, strong base salt, neither of the cations that it produces reacts with water. So they say a SASB will have a salt pH, will have a pH of a 7. So for instance, I have an LIBR, okay? So really, where that came from, because it's an acid-base reaction that makes the salt plus water, this is the salt we're looking at. We're trying to categorize which of the four does it fall under. And it's trying to backtrack to what were its parents. So this is how I work this. If I am given a salt, LIBR, and I want to work back to who the parents were, I know that this metal comes from the base. So I add an OH to it. I don't care if I'm writing the formulas perfectly, but it gives me an idea that LiOH came from this part, HBr was its parent over here. So that's a strong base, strong acid, all right, parent. So that makes it an SASB salt. None of these ions from the salt, these salts 100% ionized, none of these will go on to react with water at all, to do a hydrolysis reaction. So this is why we say a pH is of 7, because it would have been this salt with HOH being produced. So an SASB salt does not undergo hydrolysis because its parents were both a strong base and a strong acid. So therefore, the pH will be 7. There's no calculations then to do with this. It is a concept. Let's look at some other salts here. A weak acid, strong base salt. Sometimes they just call it a weak acid salt. So we're looking at KCN. And again, I'm always asking for these salts, who were the parents? Who were the parents? So I'm going to go back and put the OH over here and the H, attach it to that. So I know that that is a strong base, a weak acid. So I know then that one of these ions are going to go under hydrolysis. So remember, these are 100% salts that ionize. So I have 100% on this side. I don't even have this as a molecule anymore. Does he go on and react with water? No, because he comes from a strong parent, a strong base parent. So because he comes from a strong base parent, that does not react with water. However, the cyanide ion does come from a weak acid, so it's going to undergo a hydrolysis reaction. This is exactly what we did when we were doing bases, when you had a negative ion and you were trying to react it with water and write those hydrolysis reactions. A Bronsted base, think about this, will accept a proton. So it's going to make an HCN plus OH minus, boom, remember, write a KB because I wrote an OH minus. Get into that habit at all times. Just make it a habit, okay? So HCN plus OH minus is the reaction. So when I have a weak acid strong base salt and I was able to write this, I know that it's going to be basic. Some students will go on and memorize all of this. I don't have any of that memorized because I go through the steps. Okay, who were the parents? He's strong, he won't react. This part of the salt won't react. He's weak, so this anion's going to go on and react with water. I write my hydrolysis reactions. I know I need a KB just because I'm doing it as a habit. I know it's basic because it makes the hydroxide. Now, why is that basic? Because it also makes an acid. But the acid is weak, right? Weak acids stay as the molecule. They don't ionize, so it's not impacting the pH. If this was to go on to 100% ionize, it'd be a whole lot of mess. But because this is a molecule, I don't have to worry about that impacting the pH. So the cation came from a strong base, and the anion of the acid came from a weak acid. Those types of salts then make basic solutions. Literally, if you took the salt, put it into water, and put a pH paper in it, you would get a base pH because of this hydrolysis reaction. Let's go on. Now I have an NH4Cl, and I want to know who the parents were. We know to add the H to this part of the salt, but this is a little bit different here. This really is the base, NH4OH, but you know, like we haven't really seen that maybe. We've talked about it in the past. It really is the proper way of writing ammonia. Ammonia. We looked at it in hydrogen bonding when we did intermolecular forces, and we know that the NH3 gets attracted to nearby water molecules, and through hydrogen bonding, it really makes this I didn't draw that well. It really makes an NH4OH. Just leave it at that. So this is our base. This is the base. So this comes from a strong acid. This comes from a weak base. So it's the NH4 plus of the salt that's undergoing hydrolysis. All right, because remember, the salt is no longer the molecule. It is all ions, and we want to know, do these go on to participate with a hydrolysis reaction with water? That's what we're trying to answer. We eliminated this because it came from a strong acid. This comes from a weak base. This undergoes the hydrolysis. And I'm not even reading up here. I'm not even looking to see if it's going to be acidic or basic because I don't have any of that stuff memorized. I look at writing my hydrolysis reaction and I know that this is going to donate a proton. This is not going to go in this way and make an NH5 plus 2. If I donate that proton, this should look familiar. I said to get to know this type of reaction because it's your poster child for an acid-base reaction. So we have an NH3 plus H3O plus. Boom, I need a Ka because it made a hydronium. I know that it's going to be acidic. That's how I get there. Okay. Let's look at really kind of a special type of a salt. When we look at these parents, this is an NH4OH and this is an HCN. And actually, this is a weak base and a weak acid salt. So you can have it all. That both ions of this salt, when it dissociates into all of its ions, that each of these ions are going to go on and react with water. So let's take a look at, again, what that's going to look like. We just wrote this one up above. So this is going to be an NH3 plus H3O plus. Right away, write down Ka. The Cn minus, all right, that should look like a base reaction to you. It's going to react with water. That's going to get the H over here to do HCN plus OH minus, and I need a Kb. So right now, both of these can impact the pH, but what we need to do is to know those Kas and the Kbs. And in the back of your textbook, in an appendix, is the Kas and Kbs of all of this. So all of this is in a chart in the back of your book and in the appendix. We take a look at this to say that whoever is the largest is going to be the hydrolysis reaction that is important. And we can see that the Kb value is greater than the Ka. So this is going to be a basic solution. If I had to go on and determine the pH, this is the reaction I would use to determine it because the Kb is larger than that. So he's the one that's going to determine the pH, the pOH, everything in this solution. Once in a while, it's not that common that the Ka and the Kb will actually be identical. If they are identical numbers, then it will be neutral. They have a it will be pH of 7. It's not that common. All right, so will these be acidic? Will these be basic? I don't know. Look at that first one. They gave me the Kas and Kbs, so there must be some reason for that. Just like we've been doing, we've been trying to determine what are the parents. So this is NH4OH. This is HF. They are a weak base, a weak acid. So both of these ions from the salt are going to actually impact the pH. And just like we did in the previous example, both of these undergo hydrolysis. One needs a Ka, one needs a Kb. So we have the values up here saying that the Ka is larger than the Kb. So this is the one that's going to determine the pH. It will be acidic just because Ka is larger than Kb. I want to make sure you can write these hydrolysis reactions, so that's why I'm writing them. Because you could have just looked at the Ka and Kb and called it good. I want to make sure you understand how they're getting that. All right, let's go to KNO2. Who are the parents? KOH, HNO2, strong base, weak acid. So it's the negative ion of the salt that's undergoing hydrolysis. Just like a base, I should put an arrow, this is going to accept a proton, and this is going to be OH minus, so I'm just getting in the habit that it needs a Kb. There's nothing to solve here, other than to say that it will have a basic pH because the hydroxide ion is produced. You finish these up on this page and then check back to see if you got them correct. All right, let's take a look at making these parents. When I make these parents, it's a strong base, a strong acid. If it's that type of a salt, there's nothing to do. It's going to have a pH of 7. Come down here, NH4OH, HNO3. I know that that's a strong acid. I have it memorized. This is a weak base. We've written it enough, but this is always an equation that gets students a little confused. So the more you can keep writing it and remind yourself how this works, you're good. So this will be acidic because of the hydronium that's made. All right, let's actually solve some pH questions about salts. So let's take a look at the first one. The first thing I have to recognize that there's a salt in my beaker, because you always are saying, what is in my beaker? Well, that's a salt. So because it's a salt, I have to know who the parents are. I have to see which of these are going to undergo any type of hydrolysis. So I know that this is a strong base, a weak acid. So this part of the salt, this part is going to undergo hydrolysis. I wrote this one up here to don't forget that you can always write the acetate ion like this. So it might look like that in some equations. So the hydrolysis reaction is C2H32O-1. There's your base, right? So it's going to accept it. Becomes HC2H3O2 plus OH minus. Boom! I need a KB. We know the formula to be able to do that, and I calculated it because it only gave me a Ka. It's 5.56 times 10 to the negative 10. All right, so I have my hydrolysis reaction. I have my Kb, and write your Kb expression. Just kind of makes you take another look at what you're doing. Oh, this should be HC2O3. All right, and then over here, C2H3O2 minus 1. So what's my concentration? I have a 0.25 molar of this concentration. So here's the concept. Originally, I had 0.25 molar of this salt and 0 of this, but immediately this goes to 0. And because it 100% ionizes, this is the concentration I have of each of those ions. So when I do this, it's saying I have 0.25 molar concentration from that dissociation, 0 over here, minus a little bit X over there, add some over here. All right, and it looks like that. So I'm going to ignore that X. This becomes X squared over 0.25 molar is equal to the Kb. All right, is equal to the Kb. What is that? 5.56 times 10 to the negative 10. I've got an X is equal to 1.18 times 10 to the negative 5. But what does that X tell me? Again, it tells me a hydroxide ion concentration is what it tells me, and it wants to have a pH. So I can find pOH from this information using those original 4 equations. And this is what I have as my answer, 9.07. We should be close. All right, go on and do this problem. When I come to this, I look at this and immediately I say, what's in my beaker? It's a salt. It's not a weak acid. It's not a strong base. It's a salt. So now I need to know who the parents are. That's my next step in salts. And this is a strong base, a weak acid. So I know that that part of the salt is undergoing hydrolysis. I'm going to react it with water. As soon as I make that OH minus, I know I need a Kb. Yay, it gave me a Kb, so I don't have to calculate it. Now I want to know my initial concentrations. And how do I do that again? It's that concept that I have 0.75 molar of this salt and nothing of this. But immediately this goes to 0, and I have 0.75 molar concentration of those ions. So I now know what my initial concentration of the fluoride ion concentration is. It comes from the salt. And then I have 0 of this, minus that, add that, 0.7 minus X, X, X. I'm going to put that into my KB expression, which I did not write. All right, so I'm just going to put it in here. I like to keep to the same pattern of how I solve problems so I don't miss things. Now put x's into each of those, so this becomes x squared over 0.75 because I'm ignoring that. And I get x is equal to 3.24 times 10 to the negative 6 when I do all this, right? Because we know what KB was. All right, but what does that tell me? It tells me hydroxide ion concentration. Finish it up by going back to those original equations, and I'm going to pop it in there, and I get 8.51 as a pH. All right, let's take a look at this one. One thing I want to point out is that it looks like it might be asking a different question, but they're actually asking the same question. So these are really two questions. We've already done them, all right, but they might look different to you. What is the pH of 0.75 molar? This one gave me a F-1, so that is a weak base. And this gave me a salt. Salts, I have to do that extra step to figure out who the parents were and figure out if any of those ions are going to undergo hydrolysis. And I find out that the fluorine from the salt is going to undergo hydrolysis. So in this first one, I would have written the equation that looked like this. And I would have need a KB. That was the one that we just finished. That's the salt, right? I just did that problem. We did this on our base video lecture, and I had to write this equation to solve that problem on those lectures. What I'm saying to you is that really when they give you the base as being a fluoride ion, it really did come from a salt. But what they've done is they've given you the ion that undergoes hydrolysis. Instead of you figuring it out by doing the parent route, you had to figure out which of these undergo hydrolysis. By them giving it to you already as an ion, they've done the work for you. You just didn't realize it really did come from a salt. So salts just have that extra step to determine how that works. The parents, okay? So let's take a look. These are asking the same question. This one is giving you a salt. This one is giving you a weak base. But if we were to get this, we don't know it's going to turn into that yet because we don't know which ions yet are going to matter. So I am going to have to figure out, as the extra step of a salt, is which one of those ions from the salt will react with water. This is your weak acid, and so this is the ion that's going to undergo hydrolysis. So here I am finally able to write this equation to start my journey on being able to solve it. Immediately write KB. And of course, they didn't give me a KB, did they? I'd have to calculate that. So this one, it's already given me the cyanide ion. And look at this. It's the same equation. Now, they gave me the concentration of the cyanide ion, and you can say that's another extra step in the salt, because in the salt, we have to remember that it 100% ionizes. So this 0.15 molar, which was this salt, goes down to 0, and all of this concentration comes on this side. So for us to find the concentration of that ion, you can say it's another little extra step with the salt. So if I go on to calculate what this looks like, and I'm not sure if we had already done this in the base problems when we solved it. All right, I'm not writing my K expression here because I'm running out of room. So I'm going to write down what I have. I calculated my KB to be 2 times 10 to the negative 5. So I had to calculate that. When I solve this for x, I get 1.73 times 10 to the negative 3, and that is telling me a hydroxide ion concentration. And we've seen what we have to do when, oh, we're done, right? Sometimes you think you have to keep going on. That's all they wanted was the hydroxide ion concentration. Yay. All right, you guys all do this last one. For the salt, go through the steps and get our answers at the end. So in this one, what is my parents? Well, my parents are a strong base, weak acid. That's who they are. So this part of your salt is undergoing hydrolysis, and that's the base portion of it. And this is what it's going to make. Boom, I need a Kb. So I'm going to have to take this equation and convert that Kb or Ka into a Kb. And I got an answer of 3.33 times 10 to the negative 7 is what I got for my Kb. All right, so I'm just going to go right into solving it. I know my concentration of this is 0.1 molar, and I don't have any of this. Remember how I am getting that concentration, right? Because eventually this was 0.10 molar and it goes down to 0, and these become 0.10 molar. That's how I know my concentration. Now, if there was a 2 in front of this, I would multiply that by 2, but these are just have been 1s. I think for the most part they are 2. So a little bit of this is going to make some of that. I didn't write my K expression because I'm running out of room, and so I'm going to take my x times x over 0.10, and it's going to equal 3.33 times 10 to the negative 7 because I needed a Kb. My x is 1.82 times 10 to the negative 4. Again, what is that telling us? It tells us this information, and I can go on and calculate my pOH, and then my final pH is 10.21. That is what they wanted, yes. So these are your salts to figure out who the parents are. Once you find out whoever's the weak, to be able to write these hydrolysis reactions. When you can write an OH minus, immediately just write Kb because you know that's going to be an extra step. And to understand that these soluble salts 100% ionize into this side, and there's no molecule of the salt left.